Great. Thank you. Okay, so today we will be looking at QR decomposition and Gram-Schmidt orthogonalization. In the last lecture, we were looking at pseudo-inverse, how to obtain the solution of an overdetermined system. So in an overdetermined system, you have more equations than variables. So we don't look for the exact solution. We look at the solution which minimizes the L2 norm squared. Okay. So, and this time we'll look at another approach for the same overdetermined systems, and that is based on QR decomposition. A matrix, a tall matrix, or actually a white matrix actually, can be decomposed into a Q and an R. And then Gram-Schmidt orthogonalization is a algorithm, an approach to obtain the QR decomposition of a tall matrix. So let's plunge in. First, we'll look at full QR decomposition. Then we look at reduced QR decomposition, also called economy QR decomposition. Okay, these two terms can be used interchangeably. Then we look at how this method produces the same solution as the least square method that we discussed in the last lecture based on the pseudo-inverse. And then we will look at the Gram-Schmidt orthogonalization algorithm to obtain the reduced QR decomposition. Okay, so this is what QR decomposition of a matrix looks like. A is an M by N matrix. It's a tall matrix because M we assume to be greater than N. It has more rows than columns. And it is decomposed into this form. Q is a M by M unitary matrix. And you know a unitary matrix is one whose inverse is its transform. And then R is a M by N upper triangular. It's not really upper triangular. It's like this. This R here is upper triangular, and then I have a bunch of zeros. Now, what's the justification for this? What's the rank of A? It's an M by N matrix, and N is less than M. So the rank of A cannot exceed N. Correct? Now, what's the rank of Q? It's a full M by N unitary matrix. Its rank is, it's a full rank matrix, correct? Because it's determinative 1. So, it's an M by M matrix, correct? So, this has to be a M by, this is a M by N matrix. What's the rank of this? The rank of this is N. Okay, because N is less than M. And so it has an upper triangular matrix here, M by N upper triangular matrix. If you look at this is an upper triangular matrix R, and then we have a bunch of zeros. This R is full rank. Okay, that did that. So this is a full rank matrix, upper triangular, correct? So its rank is N, and then we have a bunch of zeros. All these are rows. Usually this means a column vector, but here I just avoided using a transpose each time. So it actually means this is here, it's a row vector of all zeros. Okay, so this we have M minus N rows of all zeros. Okay, so this is what the full QR decomposition looks like. And Q is a unitary matrix. Okay, now when we do the multiplications, okay, think of this as, this is row 1, this is row 2 until, so these are zeros at the end. Okay, how many zeros? M minus n zeros. Okay, so what are these? These Q's are what? This is unitary. Therefore, these are all mutually orthogonal unit vectors, Q's. Okay, now what is this Qm going to get multiplied with? Replace this with block vector. Each row is an element of the block vector. Okay, so this is the first row, second row. So Qm is going to get multiplied with 0, right? So instead of Qm, if you replace it with, say, negative Qm, okay, it won't change things. It won't affect the product. It'll be A. Instead of negative Qm, if you want to use some other vector, well, this might not be a unitary matrix anymore, but it won't affect the product because this is going to get multiplied with 0. In fact, a whole bunch of them are going to get multiplied with zeros. Now, this is what it looks like visually. This is the matrix A. It's a tall matrix, M by N. This is Q, and this is R. The white region is all zeros. Okay, and so these columns of Q, the last M minus N columns of Q, are all going to get multiplied with zeros, right? So here, visually, this is what it looks like. All these columns, M minus N, okay? So here, this side of Q has the same size as A. Okay, but this part of Q is getting multiplied with all zeros. So they are really redundant. They're just there so that we have a unitary matrix Q. Okay, that's in full QR decomposition, but they are kind of redundant for computational purposes. So that brings us to this. What if we just get rid of this part and this part? Okay, so this is what I was talking about. These Qn plus 1 through Qm are getting multiplied with zeros. What if we just eliminate these, remove these from the Q? So we get a Q now, a new Q, which has only n columns, not m columns as previously. The last several columns have been discarded. Yes?
In a previous slide, yeah. So in this picture, usually we take the product row multiply with the column, but in the QY is vertical from here. I didn't understand this red in the on the second side. Yeah, at that side.
Yeah.
Why this region of Q is multiplying with? Because
if you look at it element by element.
Okay.
Okay, so this is, let's take, this is one column.
Okay.
Okay, now, okay, let's look at the last one, QM.
Okay.
Okay, when we get the product, okay, what is, A will be M by N, correct? So what's the last column of N going to be? Q1 times R1N plus Q2 times R2N all the way to Qm times 0, right? That's the last column of A. So you see this is getting multiplied with all zeros, Qm.
Okay.
Right? Look at the first column. How do we get the first column of A? Q1 times R11 plus Q2 times 0. All these will get multiplied with zeros. Okay, so your question was, why is it redundant? Why is it that these are always going to get multiplied by zeros? Well, they are. Okay, if you look at each column separately, then they are. Which is why another way of looking at it is, well, I think that should be good enough. Okay, does this answer your question?
Yeah.
Okay. So now you understand why we can get rid of these. So I simply take the first the first n columns of Q, which are going to get multiplied with R, and I discard this. Okay, because it's going to get multiplied with zeros. And so what I get is this is my new Q. And this new Q is an m by n matrix. It is a tall matrix, so it cannot be a unitary matrix. A unitary matrix is a square matrix. But the columns are still mutually orthogonal and they are unit vectors. And on this side, so this Q, mind you, is not the same as this Q here. This is full QR decomposition, but this here is reduced QR decomposition. The Q, must take a note of it. I'm just calling it Q again. It's a slight misuse of notation, but it's always called QR decomposition. Okay, maybe I should have called it Q prime or something. But this Q is a tall matrix, and this R is the same R as you would get from full QR decomposition. Okay, so this is the reduced QR decomposition, and visually this is what it looks like. This is my Q, and R is now a square matrix, and n by n upper triangular matrix. Q is a tall matrix, m by n. It's not a unitary matrix anymore. It cannot be a unitary matrix. Okay, so this is the full QR decomposition where Q was a unitary matrix, ergo a square matrix, and R was upper triangular, and then it had a bunch of zeros. And now this is the reduced QR decomposition. Okay, now since Q has less columns, it cannot be a full rank matrix. So Q transpose excuse me, cannot be equal to the identity matrix. Q transpose would be a m by m, a bigger matrix. Okay, it cannot be equal to the identity matrix, but we still know that these columns of Q are all unit vectors and they are mutually orthogonal, which means that Q transpose Q is still equal to I. This I is the smaller n by n identity matrix. Are we clear? Now, how do we solve overdetermined systems using QR decomposition? Yes?
In the previous slide, so the R matrix would be same as R augmented with 0?
Yes. The R matrix of both full QR, this R side, is the same here.
So the augmented zeros will go away.
Exactly. Only the zeros have been dropped. I'm explicitly writing R0. Okay. Only the Q, I'm just dropping these columns of Q. Okay. So that makes it clear? So her question was if this R is the same in here in full QR and in reduced QR, and my answer is yes. The zeros in the full QR I'm explicitly writing down as a second block. But remember that this Q is not the same. Only it retains the first n columns of the full QR's Q. Okay, so now let's see how we can solve this overdetermined system using QR decomposition. We'll focus on full QR decomposition first. So we have this AX should be equal to B, but this is a tall matrix. We have more equations to satisfy than the number of variables. M equations, but n variables. So we cannot expect to satisfy all of them. What we will do is look for an approximate solution. And in the previous lecture, what we saw was the min norm solution, or the sum square error, minimum of the sum square error solution was x equals a pseudo inverse times b, correct? So now we're looking at QR decomposition. Okay, so QR0, remember full QR decomposition, so this Q is a unitary matrix. QR0, x is approximately equal to b. I pre-multiply both sides with Q transpose, so I get Q transpose Q times R0, x equals Q transpose b. Okay, now what is this? What's the size of R0? This is m by n. It's a tall matrix of the same size as A, right? Because I have explicitly written down the zeros. So this is a tall matrix. R0x equals, and this again, Q transpose B will have dimensionality of m as in Maryland, not n as in New York. So it's a larger vector. Okay, so what I can do is I can say that Q transpose B is C1, C2, where C1 is, so I'm writing this in terms of a block vector. C1 has the first n elements, n as in New York, and C2 has the remaining m as in Maryland minus n as in New York number of elements, C2. Okay, so this is what I have. R0x is equal to, or approximately equal to, C1, C2. I put the approximately equal to here. Okay. Now, what we can do is we can simply drop the zeros. So look at the first, let's read the first line of this expression and just ignore this Q transpose B. Rx equals C1 and 0x equals C2. Correct? That's what it looks like, right? Rx is C1 and 0x is C2. But 0x cannot be C2, right? Because 0 times x is 0. But Rx is C1. So we can attempt to solve this. Rx is approximately equal to C1. Okay, but it's actually, how many rows does this have? Remember, R is, in full QR decomposition, R is simply an upper triangular matrix. Excuse me, yeah, it's an upper triangular matrix. This is reduced, but it's the same thing in the full. R is, well, I wrote m by m, but sorry about that. It's a little confusing. I could have written n by n here, okay? That would explicitly mean only this part. Sorry about this typo. Anyways, so we'll end up with R, where R is a upper triangular matrix. X approximately equals C1. But R is an upper triangular matrix. We can always use back substitution to solve for X. It's quite an easy algorithm. Okay, and in fact, in a later slide, I'll just show you how back substitution works. So we can actually solve it. Or X is our inverse C1. This is the actual inverse. And inverting a upper triangular matrix doesn't require a order n cube algorithm. It can be done with a less complex algorithm because it's upper triangular. Okay? So X is equal to R inverse times C1. And R is upper triangular, so it can be solved readily. Okay, so this is what we have. Eventually, we want to solve Rx is equal to C1, where C1 is this upper n elements, n as in New York, elements of Q transpose B. And we can solve it readily using back substitution. So this is the full QR decomposition, and only C1 is used. So we can, since C1 is the one that's being used, okay, we can use reduced QR decomposition. This is the reduced QR decomposition, and so what we can do is, again, we're trying to solve AX equals B. We do the reduced QR decomposition of A, so QRX is, again, approximately equal to B, and so Rx is Q inverse B, or Q transpose B, which is, well, Q transpose Q is still, if you go back here, Q transpose Q is still the identity matrix. Only QQ transpose is not. Okay, so coming back here, so when we do the reduced QR decomposition, so this Q, we can pre-multiply both sides with Q transpose, so we get Rx equals Q transpose B, which is again C1. Okay, because we have eliminated the, here this had a bunch of zeros. Right? Now here it's just Q transpose B will just give you the elements of C1. And this we can solve directly using back substitution. Okay, so Rx is approximately equal to C1 we get, or X is R inverse C1. Here's an example to make it clear. So this is full QR decomposition. What we are doing is taking the full QR decomposition of A, and then we are getting this Q transpose B. This is the matrix C, okay, and I'm removing the bottom C2 part and solving for Rx is approximately equal to C1, okay. And here, in reduced QR, I directly get my C1 as Q transpose B, okay. So the difference will come to light in the next example. So this is, suppose we do full QR decomposition, okay. So I have C here, I just call it C. R0X is approximately equal to C. Here's an example. Okay, this is when I've pre-multiplied both sides with Q transpose. So R0X is Q transpose B, which is C1, C2. This is my C1 part, and this is my C2 part. 1, 0 is C1, negative 3 is C2. Okay, and this is R0. This is based on full QR decomposition. Okay, I want to equate both sides here. Let's look at the min norm solution. Okay, I take the Euclidean norm of this vector squared. Okay, and that simplifies to this. Twice x1 minus 1 square plus x1 minus x2 square plus 3 square. Where does this 3 square come from? 0 times x1 plus 0 times x2 minus of minus 3. So the third element is 3, right, in this vector or this vector. So we have this 3 squared here. The first element of this left-hand side minus right-hand side would be 2 times x1 plus 0 times x2. That's 2x1 minus 1. See that? So this is what I want to minimize, correct? And the solution is obvious here. Make these 0, which have the x's in it. And the minimum value of this will be actually 9, 3 squared. Okay, now let's look at what we would do in reduced QR decomposition. We would, instead of R0, we would just get R. right? So this is what we would solve. Let's look at the min norm solution. So I take the norm of the left hand side minus right hand side and square it. I get twice x1 minus 1 squared, and that's from the first row here multiplied by x1, x2, and then the first row. And the second row gives us negative 1 times x1 plus x2. So x2 minus x1 or x1 minus x2, doesn't make a difference, minus 0. So this term, right? Now you can see the difference here. What's the difference? This part, correct? The 3 squared is the difference. And so what we can do is, you can see that we land up with the same solution. Reduced QR decomposition and full QR decomposition give us the same solution. And miraculously, for this little example, you saw that I was using the min norm solution. Okay. This, you don't require to solve the min norms, obtain the min norm solution. No pseudo inversion is required. Okay. You can directly solve it and it will give you 0 because all these terms contain x. So you have n equations, n as in New York, n equations in n variables, n as in New York. So it's just a straightforward system of linear equations, equal number of equations and variables. So it can be solved directly. Okay, and somehow if we solve it directly, twice x1 minus 1 equals 0, and x1 minus x2 equals 0. We solve it. We are somehow getting the same solution as we would have done using the min norm approach of the last lecture, pseudo inversion method. Okay, we just saw this somehow happening for this little example. We are getting the same solutions, and these solutions somehow happen to be the same as we would get from the pseudo inversion method. So the question is this X in general? Okay, so we saw from here that we can, instead of using full QR decomposition, we can take the reduced QR decomposition to solve it. But here, without justification, we saw that it's somehow the same as the min norm solution. The pseudo inversion would give you the same X. Okay, so this is what we would get from the pseudo inverse method. B minus AX Euclidean norm squared, we're trying to minimize through X, and that is the pseudo inverse solution. X equals A pseudo inverse B. But is the QR decomposition approach, reduced QR decomposition approach now, is it going to give us this same solution? That's the $1 million question. Are you guys with me? Okay, so QR decomposition surprisingly gives us the same solution as the pseudo inversion method or the min norm method. Okay, and that's what we will look at next. It's surprising, right? So, first, before we begin with the formal investigation, I just want to, yes?
So, from full QR decomposition, when we move to reduced QR decomposition, we see that we are getting the same solution.
Yes, and that is obvious.
So it means that the reduced QR decomposition is telling us that there are redundant information which is not affecting the solution.
Yes.
In our determined system, we have a redundant information which we do not need to find the solution.
Well, again, it depends on, so his question is, in overdetermined systems, like in this one, you have redundant information, and which you can ignore. But, well, here we have zeros, but in general, if we have A here, what is the redundant solution, right? So you'll get different solutions if you just arbitrarily drop different rows.
But A is decomposed into QR.
But A is decomposed into QR, and then that QR decomposition identifies the what you can drop actually. It's okay. And so we're going to formally see that this is really the redundant information, and this alone will give you the same solution as our previous method. Okay. So here's what we are. This is a block vector AB, and it's L2 norm squared. Its L2 norm squared is the vector transpose times the vector, right? So A transpose, B transpose, that's transpose of AB, and then the vector AB itself, which is equal to A transpose A plus B transpose B, which is L2 norm of A whole squared plus L2 norm of B whole squared. So the L2 norm squared of this block vector is equal to the L2 norm of this squared plus the L2 norm of this B squared. Okay, so if you have a block vector, you can easily find its L2 norm in chunks and add them up together, the squares of the L2 norms together. Okay, here's an example. This is a vector C. 1, 2, negative 2, 0, 4, negative 4. And L2 norm of C squared is 1 squared plus 2 squared plus negative 2 whole squared plus 0 squared plus negative 4 squared. That gives us 25. Okay, now let's express C as a block vector. C1 is the first block, 1, 2, negative 2, and C2 is the second block, 0, negative 4. What's the L2 norm of C1? 1 squared plus 2 squared plus negative 2 squared, which is 9. And the L2 norm of C2 squared is 0 squared plus 4 squared, which is 16. 16 plus 9 equals 25. Okay, so this is what we have. If C is expressed as a block vector like this, C1, C2, then L2 norm of C squared is L2 norm of C1 squared plus L2 norm of C2 squared. And this we will be using in our formal investigation. Okay, so this is lemma solving Rx equals C1 yields the min norm solution of Ax is approximately equal to B. Okay, so we'll prove it formally. And what we get this Rx equals C1 from? R is equal to reduced QR decomposition of A. C1 is Q transpose B. Correct? So, proof. This is what we want to minimize when we are looking for the min norm solution. Min norm solution or minimum of the sum square error solution, right? So this is the sum square error, which is equal to the min norm squared B minus Ax norm squared, which is equal to, let's look at the full QR decomposition. Okay, we know that full QR and reduced QR give us identical solutions. Let's look at the full QR decomposition. Q times R0x squared. Okay, and why we are looking at this full QR decomposition is because I'm going to invoke one property of unitary matrices. I want this Q to be unitary. Unitary matrices preserve the norm. So now this is the general situation. This X is not the same as this X. This Q is not the same as this Q. Okay, in fact, this Q is actually this Q transpose. You'll see if Q is unitary, then you know that Q transpose is unitary. The norm of given any X and any unitary matrix Q, norm of Qx equals norm of X. That's why we say the unitary matrix preserves the norm. Okay, and we are going to invoke this property. So Vx is equal to this, I just got. Now inside, I pre-multiplied with Q transpose. Now this is akin to my X here. This whatever here is in parentheses. And this Q here is like Q transpose. So I pre-multiply both sides with Q transpose. This is a vector. Now if I multiply the vector with Q transpose, which is a unitary matrix, it's not going to change the the Euclidean norm squared, right? So this is equal to, I pre-multiply the terms with Q transpose B minus Q transpose Q R0X. Okay, and we know that the norm is preserved. Now this then simplifies to, this is my C1, C2 of the full QR decomposition, and this Q transpose Q is the identity matrix, so I'll just ignore it, R0X, which is equal to this. The first row yields C1 minus Rx, and the second row yields C2, and the norm of this squared. Now, this can be broken up into two separate L2 norm squared, right? We have a block matrix here. So this L2 norm squared is, we have a block vector, excuse me. The L2 norm of the first block of the vector, C1 minus Rx squared, plus L2 norm of C2 squared. Okay, and now, so you saw that this here is, this term here is the same as phi of x, which we want to minimize for the min norm solution. And how do we get the min norm solution? Using pseudo inversion, right? And now this cost function, phi of x, is the same here. This is the form of the cost function. And we want to minimize this with respect to x. Okay. Now, no matter how we select our x, is this C2 going to change? C2 is independent of x. In our earlier example, it was the 3 squared here. Oh, no. It's 3 squared. It's C2 squared, right? So this C2 is not dependent on x. Okay, so if we make this equal to 0, this is n-dimensional vector. So we have basically n equations in n variables, n as in New York. Okay, so we can simply solve for this, equate this to 0, and the minimum error will turn out to be C2 squared. Okay, so we make the first term, we can tweak x to make the first term equal to 0, and since it has the same number of equality to satisfy as the number of variables, we can simply solve for it to get the exact solution. And this would be effectively, so this way solving this is Rx equals C1 is the reduced QR norm method, right? And that gives us the same solution as the minimizing the L2 norm of the error squared. Okay, so the pseudo inversion method and this method gave you the same solutions. Okay, and that was what you had asked for, information, but we just wanted to formalize our observation. And okay, so and here, how do you solve this? It's easy actually to solve using back substitution. So what I'm going to do is, before we take up a couple of MATLAB examples, we'll look at an example of how to use back substitution. Okay, back substitution, I've given you the MATLAB code that I wrote for you to use. Okay, so you don't have to formally look at the algorithm, but we'll just take a look at how back substitution works. Okay, so I have this Rx equals C to solve. The C is C1 essentially. Okay, this is an upper triangular matrix. Back substitution, back, is because we solve for x3 first. And then using the value of x3, we find the value of x2. And then using the values of x2 and x3, we find x1. Okay, so from row 3, what do we get? 0. And we're taking advantage of the fact that this is upper triangular. So from the last row, what do we get? 0 times x1, 0 times x2, 3 times x3 equals negative 6. So row 3 yields x3 equals negative 2. I'm trying to solve for x. Okay, and then now we got x3, the numerical value of x3 is obtained. So now let's go up one step. That's why it's called back substitution. From the next row, we get 0 times x1 again, because this is upper triangular, so the upper elements here of x are getting multiplied with zeros. Twice x2 plus x3 equals negative 6. So twice x2 plus x3 equals negative 3, and x3 is negative 2. Correct? So that gives us this when x2 equals negative 2. Now we get the values of x2 and x3 both. Now move upwards to R1, the first row. We get twice x1 negative x2 plus twice x3 equals negative 4. And then we know the values of x2 and x3, so replace those values here. We get this, whence x1 is negative 1. So this is our solution using back substitution. You can easily write an algorithm for back substitution. And this is also the reason why inverting a lower triangular matrix or an upper triangular matrix is an easy task. Computationally, it's simpler than inverting a full matrix. Any questions with this? Here's a little Matlab demo before we go to the Gram-Schmidt method. Okay. This is a matrix. It's a tall matrix, 5 by 3 matrix. Okay, I generated it some way, and then I use QR decomposition. Okay, and this is by default. This is the Matlab command for it. It will give you the full QR decomposition. It will give you Q and R. But we know that QR should be equal to A, right? So if we multiply Q and R together, what do we get? This is what we get. Now these 0, 0, 0, 0 crop up because of numerical computation, but this QR is the same as A. Okay, so this is the output, and which I've shaded in blue just for distinction. This is the code. Okay, and you can see how it works in Matlab. And this is basically full QR decomposition. And this is Q and R. Same QR decomposition I'm looking at. This is Q. You can easily check that this is unitary matrix. I didn't show it, but Q transpose Q, if you do, it will give you the identity matrix. Q transpose, if you do, it will give you the identity matrix. And this is R, an upper triangular matrix followed by several rows of zeros. Okay, this is actually R0 in the notation. Okay, it's a little confusing, I understand. Okay? Now, this, if you specifically want reduced QR decomposition, this is what you do. a second argument 0. That means reduced, or and MATLAB terminology, it's the economy QR decomposition, it's called. And now you get this. And observe what you're getting. Oh, these last two columns of Q have been removed. But you see full QR and reduced QR. Nothing here has changed. Correct? And look at R of the full QR decomposition. All these non-zero elements are the same in the reduced QR decomposition. Okay. Now, I create a overdetermined system. I want to solve AX equals B. What will be the dimensionality of X? 3, right? This is 5 by 3, and this is 5. So I have 5 linear expressions to satisfy with only 3 variables. So we'll see how to obtain the solution X. Oops. Okay. So C equals Q transpose B. Okay. And this is the reduced QR decomposition. Okay, I haven't cleared the workspace yet, so this QR is there. Okay, and I had created a B2, but now I'm showing you the B. And now I want to solve AX equals B, or the same as Q times RX equals B. This Q and R is in the workspace from the reduced QR decomposition. This is the R, okay, and that's the same as Rx equals Q transpose B. This is C is Q transpose B. So this is my C. Okay, and this is my R. So I can use back substitution to solve it. I just here, like instead of invoking a specific back substitution algorithm, I know that inverting in upper triangular matrix is easy. So X equals in R star C I wrote, and that's the solution. X, this X, I get this solution, 1, 3, 5. Okay. Now, this was what I got using reduced QR decomposition. X equals 1, 3, 5. If I were to use the pseudo-inverse method, X equals pin A star B. Pseudo-inverse of A times B. This specs, I get same solution. Okay. Another Matlab thing. Now, QR decomposition of a wide matrix. Now, this is my A. It's actually I just transposed the matrix that I had earlier. So this is my A. Okay, and this gives me the full QR decomposition. I don't have any redundant zeros this time, okay? Mind you, this is not the same as what we looked at in overdetermined systems. This is a wide matrix, okay? These are not, you don't have 0 rows. In fact, you have some numbers here. Okay, Q is a 3 by 3 matrix, and this is a 3 by 5 matrix. So QR is the same dimension as this. Okay, and what if I put a comma 0 here? This is full QR decomposition of a wide matrix. Reduced QR, oh, I don't have that, but reduced QR decomposition would basically give you exactly the same Q and R. Okay. So, for a wide matrix, there's no difference between reduced and full QR decomposition because you don't have those zeros at the bottom. In fact, what you have is columns on the right which do carry information.
Is it an underdetermined system?
This would be for an underdetermined system. So now we move on to Gram-Schmidt orthogonalization algorithm. Okay. So, and what Gram-Schmidt achieves is a reduced QR decomposition. So, and we will look at it for a M by N matrix where M is greater than N. So, tall matrix. So, these are my columns of A. This is what the reduced QR decomposition would yield. These are the columns of A, and these are the columns of Q, reduced Q. It has N columns, N as in New York, not M as in Maryland. And this is my R, which is a upper triangular matrix. And we also know that Qi transpose Qi is equal to 1 because all the Q's are unit vectors, and Qi transpose Qj not equal to I is equal to 0 because they're all mutually orthogonal. So what I've done is the values that I need in an iteration, in a step, or that was used in a previous step, I've colored blue. And the unknowns are in red. Okay. So step 1, I need to find Q1 and R11. So in the Gram-Schmidt process, we will be moving from left to right. Okay, and there will be N steps. Each step in the ith step or the kth step, I don't remember what I used as index, we'll be, let's suppose in the third step, we'll be looking at A3, Q3, and we'll try to obtain R13, R23, and R33. Okay, so in here, A, we will be looking at, in iteration number K, we'll be looking at the kth column here. The kth column here we'll be looking at. Actually, here we'll be needing Q1, Q2, all the way until Qk minus 1. And here we'll be trying to get the kth column. Okay, so this is what we have in the first step. So A1 should be equal to Q1 times R11, right? Or A1 equals R11 times Q1. Knowing that Q1 is a unit vector, what will be the length of A1? It will be R11, correct? So R11 is simply the length of A1. Okay. And Q1 is a unit vector in the direction of A1, right? So how do we find Q1 then? Take A1, we know it's in the direction of A1, and then normalize it to a unit vector, right? And R11 is the same thing as the length of A1. So A1 divided by A1 norm is a normalized direction unit vector along A1, but we already found the L2 norm of A1, and that's R11, and so that I divide A1 with R11. Okay, so from A1, I used A1, I got Q1 and R11. That's my first step. Any questions? Okay, so this is what the steps that were involved in the first step, or the expressions involved in the first step. Here is a little example here. This is my A. Where's my cursor? Oh, yeah. So this is my A, and this is my first column of A, A1, and I obtained this. R11 is simply the length of this, which is square root of 3. 1 plus 1 plus 1, square root of that is square root of 3, and that's R11 here. And a unit vector in the same direction as A1 is my Q1. So this is my Q1. Okay, now let's move on to step 2. A1 is done. So here I will be using A2 here. Q1 we already found out from the previous step. R11 we already found out from the previous step. We are going to need to use this Q1. In fact, we are going to exploit the fact that Q1 and Q2 are mutually orthogonal to one another. Okay, so now let's write down the expression for A2. So this is what we need to find out. I've colored them in red. We have A2 equals Q1 times R12 plus Q2 times R22. Okay. Or I just rearranged this. This is what I have. A2 is a linear combination of Q1 and Q2. Q1 is already known, and it's a unit vector. Another fact is that Q2 is a unit vector, and the two are mutually orthogonal. Okay, so this is what it looks like graphically. This is my A2. This is Q1. Q2 is orthogonal to Q1, and both Q1 and Q2 are unit vectors. So this length from this point, the origin, to this head of this arrow, this is of length 1. Likewise, from here to the head of this arrow, Q1, this is also of length 1. Okay, and this is A2. What's the component of A2 along Q1? This is my A2. It's a linear combination of Q1 and Q2. So what's the component of A2 along Q1? Or the projection of A2 along Q1, same thing. It's this, noting that Q1 is a unit vector, it's cosine theta of length of A2, right? Where this is the angle theta. So this will be A2 and Q1, their inner product. That will be R12. So mathematically, we just pre-multiply both sides with Q1 transpose. So Q1 transpose A2 equals R12 times Q1 transpose Q1 plus R22 times Q1 transpose Q2, which is equal to R12. Because this term Q1 transpose Q1 is 1. So this is R12 times 1, and Q1 transpose Q2 equals 0 because Q1 and Q2 are orthogonal. So this term becomes 0. So I am left with R12. Okay, so that's how I can get my R12. R12 from Q1 and A2. Okay? Now how to find Q2? Q2 is now the projection of A2 along Q2 is R22 times Q2, correct? Okay, so now I have A1, excuse me, A2. So this is my A2, okay? And this is this vector from this point all the way to here is the vector R12 times Q1, right? Geometrically, from here all the way to here. It's R12 times Q1, this here, correct? And A2 minus R12 Q1 will give me this Y2, right? So Y2 is A2 minus R12 Q1. But Y2 is the same as this vector here, R22 times Q2. R22 will be the length of Y2, and the direction Q2 will be the same direction as Y2. All we have to do is normalize Y2 to get Q2 and find the length of Y2 to get R22. So R22 Q2 equals Y2. So Y2 I get, and Y2 can be easily found out. It's the residue after removing the Q1 component from A2. So R22 is the L2 norm of Q2 and Q of Y2, excuse me, and Q2 is the normalized version of Y2. Y2 divided by the L2 norm of Y2 is a unit vector, and that gives me Q2. Okay, so this is my step 2. These are the two expressions involved in step 2. And here is the numerical example, step 2. This is, we already found out this, and we know what this is, 101. A2 we are going to use. And so, again, R12 is the inner product, A2, Q1 transpose A2, which gives me 2 over root 3. 2 over root 3. And then R22 equals, I find the residue, Y2 is A2 minus R12 Q1. R12 I know now, and Q1 I know from my previous step, and A2 is known. So this gives me R22 is square root of 2 over square root of 3. This is R22. And now what remains is, I found out R22, all I need to do is find Q2, which is basically, I have to normalize this Y2, which is A2 minus R12 Q1. So that gives me this, 1 over square root of 6, 2 over square root of 6, 1 over square root of 6. Okay, so that's step 2 example. Any questions so far? It's trivial, right? Now let's generalize. Step K. I have in step K computed Q1 through Qk minus 1. And these I don't require in step K. Okay, but I will be using Q1 through Qk minus 1, and I'll be using the kth column here, and I'll fill up all these R's first, and then find Qk. So everything that's in red, I need to find. First, I'll find out all the non-diagonal elements, R1k up to Rk minus 1k. Then I'll compute the residue y, and then find out Rkk and Qk. So Akk is equal to this expression here, right? If you read it off, Qk equals, sorry, Ak here equals Qk, Q1 times R1k plus Q2 times R2k all the way up to Qk times Rkk. So Ri kqi is the ith term here. I is less than k. Okay, and well, I could be 1 or 2. Pre-multiply both sides with qi. So I get this R1k qi transpose qi, R2k qi transpose q2, all the way to Rkk qi transpose qk. All these terms except the qi transpose qi will vanish because q's are all mutually orthogonal. I'm considering some I which is not equal to 1 or 2, okay? Just to be clear. So this term vanishes, it becomes 0. This term vanishes. In fact, all the terms vanish because the Q's are orthogonal, except this one is equal to Rik because Qi transpose Qi is 1. So I get Rik. Okay, so Qi, I could be any of these. I multiply Qi transpose with Ak, I get each of my Riks. Okay, so Rik is Qi transpose Ak, and I can go from the non-diagonal elements only. I can go from 1 through k minus 1. I don't know what's Qk yet, right? So then what do I do for Rkk? I take the residue, Yk is the residue, after I remove all the components along Q1, Q2 until Qk minus 1 from Ak. Okay, this Yk is a vector along the direction of Qk. So this is my Yk. And I know from geometry that Rkk Qk is Yk. I obtain Yk, and then how do I get Qkk, or Rkk and Qk? Qk being a unit vector, all I have to do is Yk divided by L2 norm of Yk, right? And Rkk is the length of Yk. It is the L2 norm of Yk. So Rkk is the L2 norm of Yk, and Qk is Ykk over Rkk. Yk over Rkk. This is my kth step. And this would be what the third step, K-being 3, looks like in my example. So I have to find Q3, and these are to be found out. And these are the expressions. You can follow it, and you'll see. I found out, first I found out R13 and R23, the non-diagonal elements. And then I find the diagonal elements, R33 here, and Q3 equals normalized version of the Y, the residue Y3. So we can now write down the Gram-Schmidt algorithm. Input A1 through AN, my matrix. For k equals 1 through n, step k, what we do is I initialize Yk to Ak, and then I have a for loop where I'm going from 1 through k minus 1. So in the k step, I'm looking at Ak, I have to find Qk and all these R's. First, the non-diagonals, what do? Rik equals Qi transpose Ak. And then what I'm doing here is, it's a clever way to do it. I initialize Yk to Ak. Yk should be equal to Ak minus the components of Q1, Q2 until Qk minus 1 removed from it, right? So I initialize it to Ak, and then Rik Qi I subtract each time. And after I loop through it, it will give me this. This loop goes from 1 through k minus 1, and each time I'm subtracting an Rik Qi from it, from 1 through k minus 1. So this is the actual analytical expression for Yk, which I'll get here, right? Then what's the next step? At the end, so now I have my Yk, the actual Yk, not this Yk. Yk with all the Riks times Qi removed from it. So this is the residue, and then Rkk is the L2 norm of that, Yk, and Qk is a unit vector in the direction of Yk. So this is my Gram-Schmidt algorithm. Any questions with this? Okay, so full QR decomposition is like this. We get a full unitary matrix Q and a upper triangular matrix R with a bunch of zeros. This is Q transpose will be equal to I, Q transpose Q will be also equal to I because Q is unitary. Reduced QR decomposition, we get this, A equals, this is not a unitary matrix, it's of the same size as A, and this is a square upper triangular matrix. This Q transpose is not equal to I because this cannot be full rank. And this Q transpose Q is the smaller I equal to the number of rows of Q transpose, which is the same as n number of columns of A. This is the smaller matrix here. It's the identity matrix. And for over-determined systems, what we do is we saw that if we use full QR decomposition and then we solve for pre-multiply both sides with Q transpose, so we get Rx equals R inverse C1. This is what we have to solve for, Rx equals C1. And that yields the same as the least square solution or the min norm solution. P of x, this, and this is equal to what we saw was that if we use in the proof of that lemma, we saw that b minus ax is the same as this. And this phi of x is norm of this squared plus norm of C2 squared, and all we have to do is make this equal to 0. That's why they give the same solutions. And Gram-Schmidt algorithm we just saw. The blues are what's known. AK is being used, only AK, and Q1 through Qk minus 1, which are knowns, are also being used. All Qis from 1 through k minus 1 are being used here, and then we are finding out whatever is in red. Rik and these two. I should have stopped. Well, I overdid it, but any questions? So we can end.
So the Gram-Schmidt algorithm